So continuing on with section 16.2, finding the rational zeros of a polynomial function, let's work on actually finding the zeros. So in the previous objective, we found the complete list of possible rational zeros, but now we have to find out which of those actually work. So you're going to use the degree of the polynomial to determine the maximum number of real zeros, because you can't get more zeros than the degree of the polynomial. So if the polynomial has integer coefficients, then you're going to use the rational zeros theorem to identify the rational numbers that potentially could be zeros. Then you can either use substitution, you could plug each of the numbers into the function, synthetic division, which was developed because it's so much quicker and easier, or long division to test each potential rational zero. And each time a zero is found, that also means you've found a factor, and then you can repeat step 2 on the depressed equation. So we're going to do an example of that. And if you're attempting to find zeros, remember to use the factoring techniques you already know, because it could be that you'll need to find 2 irrational zeros by using the quadratic formula, for instance, or any of the other factoring techniques that you already know. So here's the instructions for these examples. The first one, we need to find the rational zeros list and then try and find all the zeros. So we know that the most we can find are 3 zeros because it's degree 3. So for A, let's look at our list of rational zeros. So the factors of 20 are 1, 2, 4, 5, 10, and 20. And since the denominator would be the coefficients of the leading term, which is 1, we know this is the list of the possible zeros. So I'm going to set up a synthetic division with x cubed, one of those, 8x squared, 11x's, and negative 20. So I'm going to just start working my way down my list. You can do it any way you like. If you'd rather do some random order, that's fine. I like to get together with 3 friends and we each do one at a time, and then we split the work in 4. So let's try 1 first and see what happens. We'll get 1 times 1 is 1 and add 9. 1 times 9 is 9 and add, and we get 20. 1 times 20, wow, we got a bingo on the very first try. So if 1 is a 0, we know f of 1 is 0, and we know x minus 1 is a factor of our polynomial. And then we know the other factor. We identify the constant, the x term, and the x squared term. So we know the other factor is x squared plus 9x plus 20. So x squared plus 9x plus 20 times x minus 1 equals our polynomial, since x minus 1 divided evenly and we got a remainder of 0. So we're supposed to find all the real zeros. So we need to also find zeros of this quadratic. So let's check b squared minus 4ac, the discriminant, because that'll tell you right away whether there are any real zeros. So b squared minus 4ac is going to be 9 squared minus 4 times 1 times 20. And I can see that's less than 0. So there's no real zeros of the quadratic. So our answer is x equals 1 is the only real zero of this polynomial. Okay, so let's look at the second example. And our list is different, but quite short for this guy of the possible rational zeros. So possible rational zeros are factors of the constant, plus and minus 1, over factors of the leading coefficient, plus or minus 1 and plus or minus 2. So that means our list is plus or minus 1 and plus or minus 1/2. Those are the possible rational zeros. If there is a rational zero, it's one of those four. Okay, then after you do a lot of these, you should start seeing patterns. And so I have all positive coefficients, 2x cubed, 1x squared, 2 x's, and a 1. So I can see if I put a positive number in the pocket, I'm just going to keep adding and adding and adding, and there's no possible way I'll end up with 0. So I'm going to skip trying 1 because I can just already tell that's not going to work from having done a lot of these. So I'm going to try -1 as my first try. So the 2 drops down, -2. Add 1 and -2 and get -1. -1 times -1 is +1. Add and get 3, and then -3, and this is not equal 0. So that is not one of the zeros. And in fact, now we could tell that f of -1, so let's just write that out, that's an interesting thing we know. F of -1 equals -2 because that was the remainder. So because it's not 0, we have not found a 0 or a factor of our polynomial. So we have 2 more to try. And again, because of my experience with doing this a lot and seeing that I have all positive coefficients, I'm going to try -1/2, because if I put +1/2, I'm just going to keep adding and adding and adding, and never can I get to 0 that way. So the 2 is going to come down. -1/2 times 2 is -1. -1 plus 1 is 0. -1/2 times 0 is 0. 2 plus 0, -1, and 0. So I have found the 0. X equals -1/2 is a 0. So x plus 1/2 is a factor. And then let's see what our depressed equation gives us. So the quotient has a 2 as a constant, no x's, and 2x squared. So this polynomial can be factored to x plus 1/2 times 2x squared plus 2. Well, if I factor out the 2 to the front, I'm going to get x squared plus 1 as that other factor. And we already know there's no real zeros here. That has only I and -I as zeros. So in the next section, we'll want to know about those when we're asked about complex zeros. But in this section, you would say x equals -1/2 is the only real zero. Okay, so every polynomial can be factored into some combination of linear factors and or irreducible quadratic factors. So an irreducible quadratic is one that can't be factored over the real numbers. So it has only a pair of complex zeros. So we already know x squared plus 1 is one of those. And we found earlier that x squared plus 9x plus 20 was another one that had no real zeros. So a polynomial function of odd degree, if you think about this, it has to have at least one real zero because any complex zeros are going to come in conjugate pairs. Okay, so let's do one more example. Solve this equation. Oh, so now we're not being asked to just factor, we're being asked to solve the equation. So I can see that my possible rational zeros are plus and minus 1, plus and minus 3 in the numerator, and plus and minus 1, plus and minus 2 in the denominator. So I'll have plus or minus 1, plus or minus a half, plus or minus 3, and plus or minus 3 halves. So let's see, my coefficients are 2, 3, 2, 3. And again, I see that those are all positive. So I know for sure positive 1 is not going to work. So let me try negative 1, 2, negative 2, add. No, so f of negative 1 is 2. So that is not a 0. Okay, so I've tried both of those. So let's try negative 1/2. 2, 3, 2, 3. 2 comes down, negative 1, 2, negative 1, 1, negative 1/2. So that one didn't work either. And I can see that positive 3 is definitely not going to work. And negative 3 probably not either, but it doesn't take that long to check. So let's just check negative 6, negative 3, 9. Oh, that one's not going to work either. So then let's try negative 3 halves. So 2 is going to come down, multiply, get negative 3, and then that makes 0. 0 times the negative 3 halves is 0. Add and get 2, negative 3. There we go. We found the 0. So f of negative 3 halves equals 0, and x plus 3 halves is a factor. And then let's see what our other factor is, which comes from the rest of the row here. Again, we have 2x squared plus 2. So when we factor, we're going to get x plus 3 halves times 2x squared plus 2, and that equals 0. So then we use the zero product property, or the zero product principle, to say, well, either x plus 3 halves is 0, or 2x squared plus 2 is 0. But we're only looking for real solutions. It says solve in the real number system. So we're going to get no real solutions for the second factor, but we'll get x equals negative 3 halves as a solution from the first factor. So let me know if you have any questions.